Welcome. Let's look at modeling, and we're going to write a function based on the information here. So let's read through this and see what it says. Soccer team, $30 price, the average. If there's a $30 price, then the average attendance has been 40,000. Market research indicates that for each $1 increase, so adding one, attendance decreases by 1,000. All right. So we have something to work with. There's a cause and effect here, it seems. So we're going to write this, the number of spectators at a game N, as a function of the ticket price X. That means it's this notation. So N, the number of people, is based upon the ticket price. And what we need is the math parts that make that up. And then we're going to find out if the ticket price increases to this amount, what would the number of spectators be? And of course, there could be a C of this that I just didn't have on here of what if the spectators were a certain amount, what would the ticket price probably have been? But let's work with this here. All right. That's a relatively easy one. That's just a plug-in. All right. Let's take a look at what this is telling us. And I'm going to go back to the basic kind of analyzing what a statement is or what it means, how it works together, that you may have done back in Algebra 1 or Integrated 1. And we're going to build on that for this kind of a problem. So this notation is always our result. And the result is the independent variable. Y there is supposed to be the X. The independent variable is as a result of the X, or by using the X value, you get a certain result, and that's the Y, because oftentimes we write this as Y equals, because we use X and Y's. So this one here is the number of spectators, okay, spectators, and this one here then is the ticket price. So put $ sign for the ticket price. So what we know, and I'm going to go just because I'm thinking, let's say $30 and it goes up for every dollar. It also goes down. I'm going to put $30 here, and at $30, we know that it's 4,000 people. Well, if it's $31, then it's going to be 40,000. I need to put that comma in there, right? It's 1,000 less. If it's $32, 38,000 less. All right, if we go down now from 30 to 29, that means we would probably be adding one more. So as the ticket price goes down, the number of spectators may be going up. All right. Fallacy there, of course, could be that the stadium might only be able to have 40,000, except we're told it's a large stadium, so it's probably more. So that means it could go up from there. So we were given this one, and we can extrapolate from it what the amounts are for the other ones. So what we're going to look at is a way of making an equation with this. So we know the basic amount is 40,000. Okay. This one, well, let's go to this one. This one is 40,000. Oops, I need to keep making sure I put enough zeros in there. Right. So let's go to this one. What we've done is we subtract $1,000. And then for this one, 40,000 here, we're subtracting $2,000. Let's go to 33, 37,000. So here we're at 40,000 and we're subtracting $3,000. Well, I'm going to rewrite this. Instead of 2,000, that's actually 1,000 times 2 times that we have increased the ticket price. This one, I'm going to put the 1,000 here, and it's 3, which means this one's a 1. All right. So what we're finding out here is we're putting these in, but wait a minute, on this one here, this one was minus 0 and 1,000. Or, yep, now I put the zeros in. Okay, that's better. Okay. So that comes to the 40,000. No, each of these are equal here. So now what we've done is put down the dollar amount of each ticket price. Well, there's another way to look at that. The ticket price is $30. So 0 is actually, or 0 means 30 minus $30. Okay. This 1 is equal 30 minus 29. This 2 is equal to 30 minus 28. So this thing keeps changing. Okay, but 30 minus 29 is 1. But what I want to do is find a way to account for that 1 and to account for this negative. So I'm going to actually make it negatives here, which means I need to do 29 minus 30, 28 minus 30. So the reason I'm doing that, and here is 30 minus 30, and the next one would be 27 minus 30. The reason I'm doing that is because this is the ticket price. Now, we have to find a way to say 0, 1, 2, and 3 without knowing what these amounts are. So instead, or actually I shouldn't say that, but now we might know what those are, but we don't know how much higher they are. So I'm going to rewrite this part of the equation here. It's going to be the 40,000, and then it's going to be minus x minus 30 times 1,000, because the ticket price is x, so that's actually x, $30, x 29, x 23, x 27. Okay, so we get negatives there. It's not actually this negative, because now I look back at it and I think, wait a minute, yeah, no, oh, okay, no, I'm going up with those. So I am going to be saying x minus 30 and let's get these amounts in here and get this right. Okay, so now let's say I do 35, 40,000 minus 35 minus 30 is 1,000. So I've put the ticket price in here of 35. I have, oops, let's put those extra zeros in again. So that's 5 times 1,000. So that equals $35,000. Oh no, 35,000 people. These are spectators. So at 34, we would have gone to 36,000, and at 35, we would have gone to 35,000. So using 35 here matches to get us that. So what we're doing is we're doing it so that we get, by putting the ticket price here as 35 minus 30, we get a positive number, but we're subtracting that positive number of people. So it ends up taking away from the 40,000. Now let's take a look at this one and try out this little thing that I've cut here. Okay, and so if I do 40,000, I've got that in there, 28 minus 30 times the 1,000, and this is the x, so that's 40,000 minus negative 2 times 1,000. That those negatives make it plus, so that becomes 42,000. And that's exactly what happens with 28. So we've tried it with the 35, we've tried it with the 28. So this looks like the type of thing that would be the equation we would want. We would say that the number of spectators, when based on the ticket, is equal to 40,000 minus the ticket price minus 30 times 1,000. And that would be the equation that we want, and that's part A. Now, let's review that. What I had to do here was to set this up so I could see that what was happening was 40,000 take away 0 times 1,000, or 40,000 take away a $1 increase times 1,000, take away a $2 increase or a $3 increase, and then I rewrote those zeros and this kind of a format where it became then x minus 30. I need to write down to say in a different color there, x minus 30. So all of this and all of this was to analyze how to make sense of it so I could end up putting a ticket price in there. So I could use the ticket price because I needed to base this whole thing on the ticket price, not on the increase of the ticket price or the decrease of the ticket price, which is why I could not use 0, 1, 2, 3. Plus, I don't know how much increase that is each time anyway. But this way, the variable in the equation is the ticket price. Looks like a complicated equation, but it's really not that much. This amount gives you increase or decrease times 1,000 is the number of people you lose or gain based on increasing and decreasing the ticket price. And then you sort of subtract that from the 40,000 or add it to the 40,000 to get the total number of people, which is, the number of spectators a game is the total. Now let's take a look at this one. What if the ticket prices increase to $42.50? Okay, so $42.50. So that means N 42.50 is equal to 40,000. And minus 42.50 minus 30 times 1,000. So now our next step, 40,000 minus, and for this you use a calculator, 42.50, well actually this one you can do in your head, brings us to 1250 times 1,000, okay? So actually that gives us the amount of 12,000 in here. So 40,000 minus 12,000 will give us only 28,000 people. Oh, wait a minute, I forgot a 5 in there. Hold on, let me fix that. That's 12,500 because essentially we're moving a decimal 3 times by multiplying by 1,000. And when you subtract that, you're going to get 27,500 people. And so now that means that amount of an increase going up $12.50 means you're going to get a lot less people. So unless, of course, it's some big special game that's coming and more people will pay, but for the most part, most of the time, less people will come because they don't want to pay extra money. So I'm going to write this one out as the N at 42.50 equal to 27,500 spectators. That's B. Okay, so let's take a look at another one, another type of problem. This one's not the same thing at all. This one here, you're making an equation based on, the increase or decrease. This one is not the same at all in that type of thing like a stadium, but it is an increase or decrease kind of problem. So it's still making up a function. So let's take a look at this. Modeling the volume. So the volume of a rectangular prism. It involves obtaining a formula and then finding the domain. In this sense, is what are the number of possible types of things, a number of possible answers. But in this case, we're going to focus on a few. Open box, square piece of cardboard, 28 inches on the side, cutting identical squares from the corners and turning up the sides. Express the volume as a function of the length of the side of the square cut from each corner. That's where the variable is. If it says a function of, that means that's the thing that we're using x. So we'll basically be saying f of x. Or in this case, because it's the volume, it'll be volume of x. So the volume, based on the length of that little square side, will be equal to something. Let's figure out what it is. And then we are going to find the volume if the length is 3 or 4 or 5 or 6 or 7. So we're actually going to have to give 5 answers here. This is one of those where I think it's really cool to make a nice little graphic to get an idea what it looks like. So there's my attempt to make a square. This is 28 on all sides. Okay. Now we're going to cut out an amount here. And the point of, these are all the same. And the point of this is to say this amount is x, and this amount is x, and x, and x, and x, and x, and so you get the idea. They're squares, so every one of those little, all the sides are all x's. Okay, what that also tells me now is that this amount here is 28. Take away this x amount and that x amount. So it's 28, take away 2x. So in fact, I'm going to put x here and x here. All right, now let's think about what that means here. These parts have been cut out, and then the sides have been folded. So when you fold up the sides now, we've got something that'll look, it'll be another square. Because all the sides of 28 minus 2x. That's for here and here and here, as well as there. So now what we have is a box. Okay, and for that box, in folding it up like that, back to there. So this part here is 28 minus x, and the tops are 28 minus x. Oh, I think I'm going to need to move this 28 closer to the, so they don't get mixed up. And then the width here is, oh, not that one, 28. I guess I call that depth. So what we have is the height, the depth, the length, width. This would be the width. Okay. All right, so now volume is equal to length times width times height. So the volume of x is equal to 28 minus, oh, I made a little mistake here. Just did I? Hold on, because if I fold that up, I just realized when I folded it up that actually these folds here are only x amount. So having said that, now that I've done this, this is an example of how you try to do a diagram or draw something and you have to think, oh, I have to watch out for little detail. Let me use this green to show that when you fold up that side, it's only this length. But that means I need to draw it a little differently. Okay, so it's going to actually be more like this. Okay, work on getting, I need this part here is 28 minus x. This one's 28 minus x. But I want to draw it over on this side for space. But this part's only x. So what that means is the depth or width, the length. We'll call that one the length. The length is only x. Then you have a height and a width. The height and the width are 28 minus x, but the length is only x. So that means I need to erase that part. The length is x, the width is 28 minus x, and the height is 28 minus x. So that part, all those x's means that this x here is only that smaller amount. We don't know. We're going to test it for when it's 3 inches or 4 inches or 5 or 6 or 7. So this could be longer, but it's not going to be all the way up to 28. And it might be a time when all three of them are the same, but we don't know that yet, but for sure. All right, so what we now do is we're now going to multiply this out and get ourselves a nice little equation. Okay, so if I multiply all of those, first I'll do the 28 minus x times the 28 minus x. I get 784 minus 112x plus 784x squared. Oh, wait a minute, this one's the squared here. 412. Let's see, minus. Oh, no, because I didn't include the x yet. Hold on. I am trying to jump. Okay, so I've got 112x plus x squared. Oh, watch out, because these should be x's. Okay, so come back a second, and I apologize for misleading you here. Notice that was minus 2x, so I forgot to write minus 2x. So it's 28 minus 2x on each of these, length and the width. So I need to write that here. I'm going to write that here. Those little details, so yes, we need to be very careful with them. And sometimes I do miss them, but usually I catch them before it goes too far. Now when I multiply x into these, I get 4x equals, and it's x times each. I'm going to put them in order of exponent. So it's 4x cubed minus 112x squared plus 784x. All right, little trick. This is also often acceptable too on a practical basis. Now, I'm going to end up plugging the numbers in there. This is classically the way you want to simplify it. If you're told to simplify it, or in general, you should simplify the answer. So you should get down to that. So that one is A. Okay, let's look at what B is. For B, well, what we need to do is to use each of those things. So first, when the amount that you cut out is 3 inches, yep, and the amount you cut out is 3 inches, okay? So what that means is that the volume with, when you're using 3, is 3. 28 minus 2 times 3 times 28 minus 2 times 3. Well, that's easy enough to do practically in your head. So it's 3 times 28 minus 6 is 4. Let's see, yeah. 28 minus 6 is 2. 22, I believe. Yep, so we got 22. And then another 22. So when you do 3 times 22 times 22, what you get for this one is 1,452 inches. And because it's volume, you have inches here, and inches here. You have inches, 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 inches cubed. Now, when you do it with 4, that's going to be 4. 28 minus 2 times 4 is 8. So I actually can put it here. You can do that. That's 20, and then another 20. And that's going to give you 1,600. Nice 20s, easy to multiply out. When you do volume with 5, okay, we're going to have 4 take away 10. It looks like it's 18 and 18. And you start to see some various different patterns here too. With the volume of 6, I'm going to venture to say that's 16 and 16. Okay, so if I do 6 times 2, that's 12. 28 minus 12 is indeed 16. And that's going to give us 1536 inches cubed. Oh, now what an interesting thing so far that we see. Oops, I keep putting 4s there, and I should be writing 5 and 6 there. So let's fix that. Now that's correct. And then we do it with 7 because that's the last one we're being asked to. And we take 14 away from it. Well, we get 14. And that gives us 1372 inches cubed. So notice these numbers, and what they are is in this kind of graphical range, with the top one, the highest one here. And so we have two things. One is find the volume, 1, 2, 3, 4, 5 possibilities. We've just done that. So this is actually the B answer. But it also identifies what is the most efficient cut to use in order to get the largest amount of volume in the box that you make. So this would be the most efficient one if we were asked that. That would have been a good follow-on question. So I'll say it now is, and what is it? And you determine by doing a few of them and finding out which one's the largest. And pattern-wise, you can see now that if you go to 2 and 1, you're going to go smaller. If you're going smaller that way, you're going smaller that way. If you do a few more, it'll prove it to you that the larger the cut now, the smaller volume you're going to have. So you end up with this kind of a graphical representation of it. So in both of these problems, what we've determined, and in fact, I'll do that. We've determined how to make functions based upon a certain particular variable or a certain particular unknown in the problem, or not yet actually unknown, but rather something that will change, something is changing. And in this case, that something changing was the square, the amount of the square cut from each corner. So it's these amounts here. As those change, we get changed answers. But the function is based upon whatever it would be. You can use these numbers now or back to this one to be able to determine those amounts. So these are similar type problems in one sense, even though they seem very different. The concept is still the same, that you're modeling, you're making an actual equation, and that's what modeling is. Okay, spectators in one case, volume is another, and we're using an equation to do that. Thank you for watching and listening. I hope this helps with these types of problems.